Okay, so I want to talk about why mountains ride high and ocean basins ride low. So basically, what controls elevations on our planet? And to understand that, we have to understand the concept of isostasy. Let me start off with some basic observations. The first one is the hypsometry of our planet, which is basically a histogram of elevations on Earth. I would make this is 0 kilometers, so that's sea level. 4 kilometers above sea level here, and -4 over here. And what you'll find is that there's a peak here near zero. That most of the continents lie close to sea level, with some lying a little bit below sea level, which are the continental shelves. And there's this long tail that extends out to a little bit beyond 4 kilometers. And those are the active mountain belts, such as the Andes and Tibet. And then if you go to the ocean basins, you find there's something that looks like this, okay? And not much in between. And so this region, these are the continents. Okay, the tail are the continents being born, and when they stabilize, they're down here at sea level. And then over here, those are the ocean basins. And so we're always interested in why it's bimodal. Why don't we have things in between? Which is for another lecture. But let me also make show another observation. First order observation is that if I plot elevation, I'm going to call it little h elevation, and plot it against capital H, which I'm going to call crustal thickness. Okay, and crustal thickness is the distance from the surface all the way down to the seismic moho, where there's a fundamental change in the composition of the rock and the density and the seismic velocities as a consequence. And what you find is that there is a positive correlation. There's a lot of scatter, but overall it's a positive correlation. This is 0 kilometers at sea level. Okay? And at 0 kilometers, this corresponds to about 30 kilometers in crustal thickness. And then if you go up to high elevations, say 4 kilometers, like Tibet, you'll find that the crustal thickness is something about like 60 kilometers or more. If you go to the ocean basins, now here if you plot only the depth to the axial ridge, the mid-ocean ridges, you'll get something like 2 to 3 kilometers for 10 kilometers of crustal thickness. Okay. Most ocean basins lie lower than 2 to 3 kilometers, like 4 kilometers, and that's due to thermal contraction and subsidence, and we'll talk about that later. But for this lecture, I'm not going to worry about that. So when you see that there's this positive correlation between elevation and crustal thickness, then you might think we got the view we're looking at something like this. This would be like an iceberg floating in water. Just the concept of the iceberg, and you see that it's like floating and there's a little bit sticking out. What it really means is there's a really thick root underneath. So mountain belts are underlain by thick crustal roots, and we're going to get to the roots of that in a second. So this is like an iceberg, but I'm going to call this the mantle, and this is the crust. And the mantle is made out of peridotite, an ultramafic rock. So here's its density. And the crust is made out of felsic materials. So we have feldspars and quartz, which are low density minerals. And so the density of the mantle is greater than the density of the crust. And so then the crust essentially floats on this fluid substrate, the mantle. And by fluid, I mean a rheological fluid. It's all in the solid state, but if you wait long enough, for 100,000 years, it behaves like taffy, like the fluid. Okay, so it literally is floating on top. But why does it float? So to understand that, and all this elevation is h, and the whole thickness right here is capital H. Okay. Now, to understand this, we have to think about pressure. Okay. Pressure is a force per unit area, right? Newtons per meter squared, which is equal to a Pascal, right, in terms of units. And if you wanted to calculate the pressure of the overburden above you, like a column of vertical distance z and a cross-sectional area A, what you would do is calculate the weight of this entire overburden and divide by the cross-sectional area. For example, say you're sitting down there, you want to calculate the pressure and to see how much your head hurts by that overburden. And so the pressure would then equal the mass times the gravity divided by area, but mass is of course the density of this guy, this rock, multiplied by the volume, G over A, and density volume would be A, right? The area times Z, G over A. So basically pressure, you find rho G Z. Okay. In reality, it's this rho G dZ. But if we keep rho constant and G constant, then we'll just look at this one right here, rho G Z. So now what I'm going to do is make another plot. In this case, I'm going to have pressure on the x-axis and Z on the y-axis. And if you go back and look at this equation right here, which is pressure as a function of Z or depth, then the slope of this line is actually rho G. And G, we know, is always constant, and around that we're interested in here in terms of depths. So the slope really is going to be scaling with density. And so if the mantle has a higher density than the crust, then the pressure gradients within the mantle are going to be steeper. They're going to rise faster for a given depth than the pressure gradients within the crust. Okay. Now, I have drawn this PZ plot very carefully, actually, or I tried to be careful, because I did it so that the 0 point corresponds to the surface of the high elevation crust. And then this corresponds, you can think of that as sea level. By the way, obviously there's crust above the mantle and there's ocean above the mantle, but we've just going to ignore that, because once I show you how to put this together, you'll get the general idea of how you would incorporate those other layers fairly straightforward. My main goal is to keep things simple. Okay, and then I'm going to draw another dashed line. This will be relevant very soon. Okay. So the pressure, I'm going to call this C, right, and this M. The pressure under M will be 0 above sea level because there's nothing there. So at sea level is the point, it will stay 0 the whole time, and then it will increase in pressure with depth and keep on going. The slope of this line is simply rho M times G, right? Now if I go to the crust, it starts off at 0 at the top of the crust, which is higher elevation, but there is a finite pressure even above sea level because you have overburden. But the gradient is going to be shallower than that of that you would see in the mantle. And so you expect this curve to actually intersect. Let's see if I can draw this without shaking my hands. And here, okay, I didn't do a good job, but I hope you get that point here. And they will intersect right here. And the slope of this line is rho C. And above this, we're going to call where they intersect, this is the compensation depth. Okay. And above the compensation depth, the pressure in the crust, you see this, is greater than the pressure in the mantle for a given depth. That is to say, if I'm comparing here and here, right? Pressure here and pressure here is greater. Same thing here and here. Okay? But once I get to the compensation depth, the pressures are equal. So right here and right here, and right here and right here. So below the compensation depth as well, the pressures are equal. So that's a very profound result. If the pressures are equal at the same depth, at the compensation depth or greater or deeper than that, that means there are no lateral pressure gradients, and so there can be no mantle flow. Okay, and as a consequence, this crustal block, which we're going to assume for now is rigid, is what we call isostatic equilibrium. It does not move. It will not be pushed up or pushed down simply because there's no flow in the mantle beneath it. And so the concept of isostasy, that word, iso means same, and stasy means static, not moving, is basically this. It's not moving. Okay. Now I could take the scenario where if I did something like oh, I guess I should also plot here before I get to that. Let write the delta P, where delta P is rho or density pressure in the crust minus pressure in the mantle. Okay. As I said, it starts off with a zero pressure difference at the top of the crust. The pressure in the crust is greater than that in the mantle, and it will look something like that. And it will collapse to zero at the compensation depth. Okay, so this is the lateral pressure gradient. Down below here, no flow. Okay, I'll show you an isostatic equilibrium. Above the compensation depth, the pressure, there is a pressure gradient, a lateral pressure gradient, which actually will cause the continental crust to actually flow outwards. So this, we want to do something like that. Okay. In fact, this is why you may want to keep building your crust thicker and thicker and get higher and higher elevations, but eventually the pressure gradients that push outward will eventually cause your big mountain to gravitationally collapse. This is exactly why Tibet can't get higher than it does and forms a plateau. Okay, and of course it depends on rheology and all of those things. We'll talk about that later. Now let me get back to this diagram of the isostasy of this floating crustal column. I could consider a case where I push my iceberg or crustal column or rubber duck, if you want it down, just force it down below where it's not in isostatic equilibrium. And what you would do is, here's again the crust and here's the mantle, and I'm going to calculate the pressure. In this particular case, I could draw the mantle would do something like this. Okay, this would be the mantle, steep one, but the crust would actually, because it's lower density, would have go off on a lower slope up to the base, and then at the base, it would become parallel to that mantle. But this would be underneath C, this would be underneath M. As a consequence, delta P here, if I were to do that, would be, if I did zero, it would always actually be negative. The pressure, or if I did PC minus PM, it would always be falling on this side. Okay, it looks something like that. In other words, if I were to compare here and here, the pressure here is greater than over here, as well as up there. So that you will have flow, mantle lateral flow going in, okay? And that essentially will cause this whole thing to be pushed upwards. and finally to the point where there will be a point where in the mantle pressure gradient goes to 0. Conversely, if I were to put my crust, and you should do that as an exercise yourself, way up above the mantle, sitting on top of the mantle, the reverse would happen, and it would want to collapse down and sink. Okay, so everything wants to push you to this isostatic equilibrium, and we know that we are more or less in isostatic equilibrium on Earth over long enough wavelengths because this nice correlation between elevation and crustal thickness, as well as the fact that when you fly an airplane over and measure the gravity field, the free air gravity, there's no difference between continents and oceans. There's no excess mass, excess gravity beneath the continents and oceans. Okay, so let's go back to this compensation depth here, and let's try to calculate then what the elevation is and how that correlates with crustal thickness. So what you do is you'd calculate the pressure at the base, every point laterally beneath the at the compensation depth, and they would have to be equal. So in the crustal part, it would be rho C G crustal thickness equals H, right? And then in the mantle part, it'd be the density of the mantle times G, and times the thickness of the mantle to the compensation depth, which would be the crustal thickness minus the elevation that it sticks above the mantle. Okay, we can rearrange all of this, and what you'll get then is an equation where H equals rho M minus rho C over rho M times the crustal thickness. Okay, and this quantity, this whole quantity in parentheses right here, is essentially the relative difference in density between the crustal column and the surrounding mantle. And so if you go back to my plot here of elevation versus crustal thickness, well, the slope of this line essentially is the, if I call this thing a delta rho over rho, okay, this slope is equal to delta rho over rho. Okay. Now, this equation is telling you that elevation is controlled both by the density contrast and crustal thickness. It turns out that crustal thickness is far more important based on our observations. Variations in composition between continental crust and oceanic crust, although one is basalt and one is andesitic, the density differences are not that strongly different to change this much. Now, we do see some deviations from this at times, and we'll talk about that more, but that could be related to temperature effects that cause thermal expansion or contraction that change the density of the mantle or the crust. Okay, and so you could have in isostatic equilibrium something like that, right, which would fit this equation. But if it were hot here, then I might have an additional density contrast here, of alpha delta T. You'd have to account for that, and that would cause this to rise up to be a little bit higher. You can still solve this in an isostatic approach because you would just put your compensation depth further down to accommodate for the hot thermal anomaly. A scenario like this is often referred to as Pratt isostasy, which would be lateral variations in density, either caused by composition or more likely temperature. And then the iceberg scenario that I've been talking about, that's where the elevations are compensated by a low density crustal root, would be called area isostasy. Okay. isostasy. Okay, so I hope that helps explain why mountains are high, ocean basins are low, and even why mountains can't stay up high forever, because there is this finite lateral pressure gradient in the crust that will cause it to want to try to gravitationally collapse.